No. Greetings, ladies and gentlemen. In our continued exploration of, exploring, of exponential and logarithmic functions. I swear I wasn't planning on just reading that. Today we're looking at exponential growth and decay and being able to use logarithms to solve specifically for the t, the time component within those situations, because the t in exponential growth is typically always in the exponent. So here we've got a little story. It says, paleontologists study life of past geological periods, studying fossil remains. They use carbon-14, C14, which I believe if you've taken chemistry, doesn't carbon have 12?
Yeah.
Right? What are those, protons, electrons? Electrons, right? I think I'm pretending to be smart. To estimate the age of fossils. So this is actually a radioactive version of carbon, and it decays with time. I believe slowly it loses those extra electrons at a set rate until it becomes carbon-12. So this is the premise, is that it takes 5,760 years for half of it to decay, and then another 5,760 years, and another half of that amount will decay. So it's half, and then half, and then half, right? So it's always halving. Right. Arguably, it's approaching an asymptotic relationship. However, at some point, you won't be able to divide in half that one last carbon-14, right, molecule or whatever. So, right, conceptually, it's an infinite amount of time for it to lose all of it, but obviously, that in real life practicality, that would not be the case. So it says just half of the mass substance will remain. All right. This period is called a half-life, the amount of time it takes for half of its amount to decay. All right. To find the age of a fossil, with just 1/5 of the carbon-14 remaining, paleontologists must use the decay formula for this substance. So the formula for exponential growth and decay is going to be y equals NE to the KT, which I just want to point out is very similar to this formula, A equals P times E to the RT. It's actually the same. The same, all right? Just different variable names. So, right, I don't have a principal amount, but N would be the initial amount. Actually, I guess I could define some of these. So Y is the current amount, I guess, or ending amount. All right. N is the initial, and K ends up being the, somewhat of the rate, I believe. Right. Wait, would it be? Yeah, I think. Wait a minute. What's going on here? Why am I confused? Yeah, K is the rate. Yeah, it's got to be. So let's plug stuff in, define things, solve things. So for us, since 1/5 of the carbon-14 remains, you could have y equal 1/5, and you could have n equal 1. All right, you could do that, and that would be fine. That's what we're going to do. Aha! I'm jumping ahead of myself. First, I've got to figure out, for this particular element, I want to figure out how long, what's K for its half-life. Okay? So, K is going to be constant depending on the element it is. Okay? So since I know half of it ends up, right, y would be 2 if n is equal to, y would be 1 if n equals 2. Or you could say y is equal to a half when n equals 1. Let's first figure out what happens in 1/2 life. We'll solve for this k rate, okay? So, and we'd have time is the 5,760 years. So I got to solve for k before I can actually answer the question regarding the 1/5. My apologies. All right. So it's up to you whether you want y is 1/2 and n equals 1, or y is 1 and n equals 2, as long as your y value is half of the amount of your n value, for starters. So let's solve this situation. Let's plug it in. So we'll have 1/2 equals 1e to the k, and then time is 5,760 years. Right. 1e is the same as just e. I think I would solve this by ln'ing both sides. And there's my capital Ln showing up. I knew it would at some point. Yeah, that's an ugly n. And there we go. So I'll have ln of 1/2, or ln of 0.5, whatever you'd want, equals, I could pull this exponent out front, so it'd be k times 5,760 times ln of e. Oh, there's my lowercase ln showing up. I guess that's somewhat of a bingo there. And what is ln of e?
Doesn't it just cancel because they're opposite?
Well, ln of e would be asking e to what power is e, right? Log base e. E to what power is e? It would be 1. So yeah, in a sense, that we can just ignore that because multiplying by 1 doesn't affect anything. So to solve for k, I would divide by 5,760. 5,760. And I'll end up with k equals, so I'll have ln of 2 divided by 5,760, and I get 0.3 zeros after the decimal, 12034 roughly. All right. So that's our k value for our particular situation, since we happen to know what the half-life was. So now I'm going to do a separate problem regarding the specific fossils. So this kind of was a situation for all carbon-14, but now let's figure out for our specific fossils. So in our case, we've got 1/5 of the carbon remains when n was equal to 1. And I know k is now this 0.00012, and I'm looking for time. I want to know how long ago was it that this would have been, have its full saturation of carbon-14. So let's plug it in the same formula. So 1/5 is equal to 1 times e to the 0.00012t. So I can then ln both sides. It's really the same exact step here. ln. ln of 1/5. I guess I'll parenthesize that. Equals 0.00012. Let's see. 12t times ln of e. And ln of e, once again, is 0. So now I can solve by dividing both sides by 0.00012, 0.00012, and I will get my answer. T equals ln of 1/5 divided by 0.000. Actually, I might just do second answer since I still have this in here. So mine will be more accurate than the written work attests to. And I end up with t equals, wait a minute. You know what? My k value was negative. Was my k value negative? Well, either way, it's just off by a sign. 13374.3058. So it turns out that this particular fossil would have been 13,000 years old, is the idea. So the premise here is that although that the rate had been constant over those 13,000 years, so that's what, I mean, if you happen to have a large exposure of carbon, or if somehow it got diluted in some capacity, it can throw off the calculation. But it's an interesting way to try to timestamp different things like that. And that's what our whole paleontologist, system, being able to carbon date things. I think they actually have some other elements they use as well, but I don't recall. So they do have additional tests, I believe, that they're able to use. But that's the idea. So let's consider one more problem today. I think I'll do a growth situation. Bacteria. So yeah, you don't have to write down this problem, but we'll just write down our variables. And this is what we got. Bacteria usually reproduce in a process known as binary fission. Wow, that sounds awesome. In this type of reproduction, one bacterium divides, forming two bacteria. Okay. Under ideal conditions, some bacteria can reproduce every 20 minutes. Find the constant K for the growth of these types of bacteria under their ideal conditions and write the growth equation. So, let's figure this out. So what are our variables going to be? So our y, so 1 becomes 2. All right, so y is 2, n was 1. So this one's doubling every 20 minutes. T equals 20 minutes. And I guess it would be important for us to realize that our time period is measured in minutes. So, let's solve for k. Looks like what we're going to end up doing. So we'll have 2 equals 1 e to the 20k, or k20, whatever you want. And you guys ought to be used to this by now. Let's ln both sides. If you wanted, you could log both sides, but I see base e, and I'm just like, man, let's ln this. Actually, taking log base 2 would make sense as well, potentially, because that would cancel out with the 2. So I'd have ln of 2 equals 20k times ln of e, and then I'll divide by 20, because ln of e is 1. And I will get k equals...
And sorry for the interruption. Today we are operating on Schedule C for Charlie. Instead of going to an assembly at 9:28, you will go to your class meeting places for your stump speeches. The second announcement is if you are a marshal or an usher, you should come to the student service office and get a slip to leave at 9:40. Thank you.
So here's our k value, so that means our equation is going to be y equals n e to the 0.0347 t. Is our equation for this particular type of bacteria, where t is measured in minutes. So now I could ask a follow-up question, such as, how long does it take, or how long until one bacterium becomes, I don't know, how many bacteria do we want to see? 10,000 maybe? That sounds interesting. And recognizing that our how long is going to be measured in minutes here, maybe we'll end up converting it to something else if it ends up being a lot of them. So how could I figure this out? What do I do? What do I do, friends? This bacterium's lonely. How long until it's having a party? What do I do? What are my variables? What's y? 10,000. N, the starting value is 1. One lonely bacteria. And K is already defined, 0.0347. And T is what we're looking for. 1 is the loneliest number that you ever knew. So here we go. This lonely bacteria starts multiplying. Tell you what, Mr. Bacteria, we will ln both sides. No kind of party like a logarithm party. Here we go. ln of 10,000 is equal to 0.0347 t times ln of e. But this bacteria is not going to be lonely anymore, is it? Oh, snap. Okay, here we go. Divide. Actually, it's funny. The population is multiplying when he's dividing. Isn't that unusual? ln of e, of course, is 1. And I get time is ln of 10,000 divided by 0.0347. And I get 2. Do you guys have an estimate for this? Do you have any idea how big this would be? 2, 6, 5.4277 minutes. Oh, wow, that's such a bingo. Wow. Yeah, it's always the leading one that's the loop-de-2. What if I wanted to convert that into hours? Divide by 60. And so that's the same as 4.4238 hours, if you were wondering. You better make a Facebook group, start inviting people to his party, because it is going to be awesome in 4 hours. It is going to be awesome. So, here you go. So that's our concept, exponential growth and decay. Population models are often, such as this bacteria case, often modeled by exponential growth. Even real-world, right, animal populations or human populations are also modeled by that. However, at some point, exponential growth no longer effectively represents, right, so here's, right, your population over time. It does have an exponential growth curve. However, in real-world situations, at some point, it might level out and even approach some sort of asymptote, which is the limitations of the resources available to that population. So, for instance, at some point, humanity cannot have, 300 billion people on the face of planet Earth because there just won't be enough space or food for all of those people. So, due to some sort of, resource limitations, whether it's space, food, whatever, your population won't be exponential forever. And actually, most any math model, usually its accuracy is only effective within close ranges of the actual data. If you extrapolate too far, oftentimes that model becomes less and less accurate and more absurd. So, all right, friends, internet buddies, I think we're good. Population growth, yay!